several major automobile companies, including Honda, Ford and General Motors, are now adopting Tesla's EV charging technology.
This game-changing advancement has the potential to transform the future of electric cars. Let's dive deep into the explosive breakthroughs in the Ford automobile sector. Ford's creative departure from typical electric motor designs that rely on rare earth magnets is appreciable. This is not only a bold move in the face of industry standards set by EV titans like Tesla, with their high-performance Model S and Model X, but also a direct challenge to General Motors and their versatile Ultium battery platform, powering vehicles ranging from the Chevrolet Bolt to the GMC Hummer EV. The US consumers and politicians remain divided on whether to move forward full throttle with EV production, but Ford CEO believes EVs will take over the roads sooner rather than later. He conveyed an important message to those who wanted him to. No one in America builds more heavy-duty trucks than we do, and we need to bring them over land. Ford Motor Company President and CEO Jim Farley said, "Building a digital economy here in the US requires mining and processing. We cannot continue to import batteries and rare earths from overseas. We must move them to America or reduce them to maximum extent possible. We're going to invest," Farley continued, "but we need people to work with, governments to improve mines, processing, research on green tech, and support sustainability. You can build all the plants, but what good will it do if you import batteries? Technology using electric motors without magnets?" Ford has taken a proactive approach to understanding and minimizing the issues associated with rare earth elements in vehicles. They began by assessing the amount of rare earth elements in the vehicles and where they occur. This is, in fact, a very challenging task, because rare earth materials are used in small quantities, in a large number of components, and by suppliers far upstream in the supply chain. It is estimated that approximately 0.44 kilograms of rare earth is used in a typical conventional sedan, with approximately 80% of the rare earth contents in magnets. Conventional vehicles primarily use neodymium, which is used in batteries and magnets, and cerium, which is used mainly in catalytic converters. Relatively larger amounts of rare earth materials, primarily neodymium and dysprosium, are used in full hybrid electric vehicles. A typical HEV sedan with a nickel metal hydride battery uses approximately 4.5 kilograms of rare earth metals. HEVs with lithium-ion batteries contain approximately 1 kilogram of rare earths. Ford is still evaluating the rare earth content in plug-in hybrid electric and full battery electric vehicles. Ford's primary focus in addressing rare earth elements thus far has been to reduce them in the electric vehicle battery systems. Their third-generation hybrid system significantly reduces the use of rare earths compared to nickel metal hydride batteries and other lithium-ion battery systems. Ford has reduced the use of dysprosium by approximately 50% in the EV market, in the electric machine permanent motor magnets used in the hybrid systems. This new technology reduces the cost of our hybrid systems by 30%, largely by reducing the use of dysprosium, which is the most expensive rare earth element used in electric motor magnets. The new system is also 50% lighter and 20 to 30% smaller than previous generation hybrid batteries, contributing to better fuel efficiency. We expect this new hybrid battery technology will save up to 500,000 pounds of rare earth metals annually. So what's the importance of this innovation? Ford's magnet-free electric motor uses electromagnetic induction to generate rotational force. This process is more efficient and results in less energy being lost as heat. Magnet-free motors produce less electromagnetic interference, making them suitable for use in areas with sensitive electronic equipment. This advanced variant is a separately excited synchronous motor, is an alternative to permanent magnet synchronous machines, the motors most frequently used in electric vehicles. Those standard motors are based on magnets that require rare earth materials, causing reduced or no rare earth metal usage. Magnet-free motors use fewer rare earth metals, aka rare earth elements, which can help reduce the impact on natural resources and environmental exploitation. Rare earth elements are a set of 17 chemical elements in the periodic table. Though many of these elements are not actually rare, their geochemical properties make it difficult to find them in concentrated forms that can be extracted for use easily or economically. Rare earth elements have been used in conventional internal combustion vehicles in small quantities for many years. However, electrified vehicles, including hybrids, plug-in hybrids, and fully electric vehicles, use larger quantities of rare earth elements in magnets in their electric motors and in their more complicated battery systems. As electrified vehicle production increases, the importance of the supply and production of certain rare earth metals is growing for automotive companies. These elements are also used extensively in non-automotive applications. So, let's see how this technology could disrupt the existing market dominated by electric powertrains, from exciting startups like Rivian, Lucid, and NIO. Ford's approach to sustainability through magnet-free motors may affect broader trends in electric vehicle technology, as well as what it means for the future of green transportation. Rare earth elements pose both economic and sustainability challenges. The growing demand for rare earths has called into question future supply and material costs. They are also a concern due to the geographical concentration of supply and environmentally unsustainable mining practices. With our technology, we can replace the magnets and yet have the same performance as the synchronous machine, where the electric current would create a magnetic field as good as magnetic and better than a synchronous machine, where the other types of electric meters. Jim Farley added, this would have geopolitical benefits, such as not relying on China for the precious metals needed for the magnet-motored technology. With this magnet-free e-motor without rare earth materials, we have another innovation with which we are consistently improving our electric drive portfolio to create even more sustainable, efficient, and resource-saving mobility. This uniquely compact electric motor without magnets is impressive evidence of our strategy to make e-drives more resource-efficient and sustainable, primarily through efficiency improvements. Conventional SESMs take up around 90 mm more space axially, so manufacturers generally cannot flexibly vary between PSM and SESM variants in their model planning without additional effort. ZF will be compensating Ford for the design-related disadvantages of common separately excited synchronous machines to offer the advantages of separately excited synchronous machines competitively. In particular, the torque density was significantly increased with an innovative rotor design. According to the company, the space-neutral integration of the exciter into the rotor means no axial space disadvantages and an increase in power density in the rotor, which leads to improved performance, according to the company. Don't forget to like, share, and subscribe. Until next time.